Hi, everybody. Thanks, Shachar, for the introduction, and thanks for the opportunity. I would like also to thank you for staying until now to listen to my talk. Just to emphasize on this alignment, actually, like this talk is about my PhD research, as Shachar mentioned, that I have completed 2 years ago, advised by Professor Shachar in Technion, and since then, I continued in low year with this research while I'm working at Mobileye. And another alignment that I would like also to emphasize, actually, like based on the previous talks about neuromorphic computing, here by neuromorphic, I don't mean like spiking neural networks or time encoded or event-based neural networks. Actually, here I am like focusing on like analog and memory computing that potentially like could be used for artificial neural networks accelerators. Okay, so data converters are ubiquitous components in sensory nodes and in edge devices. Analog to digital converters convert analog signals from the real world continuous time domain into the digital processing domain, and vice versa for a digital to analog converter. Analog and memory computing, which aims to accelerate artificial neural network computation at the edge or at the sensor with low power consumption, actually interact with the digital modules, with the digital post-processing by means of data converters. So by that, like moving the bottleneck from data movement into data convergence. So in this talk, actually, this talk will introduce innovative approaches of the main elementary building blocks of analog and memory computing, which are memristors and data converters. So because data converters are mixed signal systems, they can be evaluated using metrics from both domains, like from analog and digital. There are several characteristics to determine their performance, but the main three are a resolution, which is represented by the effective number of bits, ENOB, a convergence speed represented by the sampling frequency, and the power consumption. Those three metrics actually collectively determine the figure of merit of the ADC, which is a numeric quantity that is fairly used to globally compare between a performance of different data converters. So based on a survey that we analyzed from Stanford University, which like it is a database that contained several data converters that were published in the top tier ICC and VLSI symposia during the last 2 decades. We can see that unfortunately there is a tremendous speed power accuracy trade-off in conventional data converters. For example, here we can see that increasing the sampling frequency will definitely decrease the effective number of bits and ultimately increase the power consumption, while in order to add an extra bit, we will pay an extra power to attain a certain speed. This trade-off is captured by the following figure of merit formula that takes into account the ENOB and sampling frequency and the power consumption. Okay, so this trade-off actually become a chronic bottleneck in the design process of data converters. Like widely commonly used data converters that are like industrial, they are customized for special purpose applications, as could be seen from this diagram that maps the different architectures into their applications. For example, for high speed applications, like the best fit is like Flash ADC or pipeline ADC. And for high accuracy, for example, for audio, Sigma Delta is the best choice. And for low power IoT devices, for example, SAR ADC is the best. So like these architectures are specific. They have exhaustive manual over-design flow, lacking a standard automated flow. Okay, so based on the same survey that I showed before, let's take a look now on the evolution of the performance of data converters along with the technology downscaling. So we know, according to Moore's law, that the digital circuits improving, like transistors become smaller, cheaper, faster, and consume less power. But on the other hand, the analog behavior dramatically degraded due to process variations, device mismatch, thermal noise, and jitter. So here we can observe the slowdown in the improvement of the figure of merit. And actually, this talk will introduce an innovative conversion paradigm based on memristive neural network ADC architecture that could potentially obtain 2 orders of magnitude better in terms of figure of merit. Just to emphasize that our rough estimations actually consider only passive elements. They exclude the active elements of the ADC. So motivated by the trade-off that we saw, by the applications diversity, and by the real-time variations, we propose like trainable data converters that could take advantage of the converted data and build like data-driven or data-aware converters to be trained in real time, to be adaptive, like to autonomously adapt to changes in full-scale voltage and number of bits, sampling frequency, as well to process variations and nonlinearities. We propose to use gradient descent and training algorithms to train our ADC, for example, by providing the labels by using like supervised training. So if we consider the conversion task as a classification task, then this could be easily solved by using neural networks. For example, like let's take a look on this special topology of neural network that implements a 4-bit ADC with full-scale voltage of 16 volt. So here, every triangle here represents a decision-making neuron. It's simply a comparator or a comparator function, and D3 is MSB, D0 is LSB, Vn is the analog input, and Vref is a reference 1 volt. Like this is an example only for illustration and simplicity. Actually, this architecture works successively from the MSB into the LLSB, similarly to the SAR ADC operation. So for now, let's run an example together and be convinced that this architecture really implements an ADC with these specifications. So let's take a look. For example, let's try to convert 7 volt out of 16 volt. So the equation of the MSB will be 7 volt multiplied by the corresponding weight, which is 1, minus 1 volt multiplied by 8. The result will be minus 1, which is like negative. So D3 is a logical 0. Then D3 will be propagated to D2, and now the equation of D2 is in the same way. It's 7 volt multiplied by 1 minus 1 volt multiplied by the corresponding weight, which is 4, and minus 0, which is the result of D3 multiplied by 8. The total result is 3. It is positive, so it is logical 1. If we continue in the same way, we will obtain the following equations of the LSBs. And we can see here that 7 volt out of 16 volt is quantized actually to 0.111. So the question is, what if we want like different specification to be supported by this ADC? for example, to change the full scale voltage to 8 volt instead of 16 volt. So all we have to do without any architectural modification, all we have to do is to change, to update the weights here that are implemented simply by resistors into half of their original values. And now 7 volt out of 8 volt will be quantized into 1110. So this network actually is deterministic, but the real-time silicon is not deterministic. It actually has a lot of like process variation and device mismatch, which make the problem non-deterministic and challenging to be modeled. So how could we compensate for these on-chip device mismatches? So we need such a variable resistor that could be updated and reprogrammed on-chip using a training algorithm. So we need a variable resistor, which is called a Memristor. So for the next slides, I will go over our journey actually to seek for this Memristor that fit our ADC application especially, and for analog and memory computing in general. So the last decade has witnessed like a breakthrough technology in memristive devices, which are like two-terminal passive elements that are based on resistive switching. Various technologies abide into this memristive definition. And for example, resistive RAM, MRAM, and phase change memory are of particular interest. They are considered promising to efficiently implement the vector matrix multiplication or the multiply accumulate, which are the bottleneck computations of artificial neural network in the analog and in the physical level using fundamental laws of Ohm's law and Kirchhoff laws. So by that analog and memory computing propose like to move the spotlight from the von Neumann, the standard, the conventional von Neumann machine, which is separated, like memory and processing units are separated, into analog and memory computing, which are like the processing and memory are co-located, inspired by the brain. So this is why it's called neuromorphic. So memristors are promising, they are emerging, but they are still not mature enough to gain like practical value for neuromorphic systems, especially for the integration, very large integration with CMOS process. Most of the reported memristive devices were integrated with selectors to add reliability, but in penalty of power, area, and control complexity. The commercialization of neuromorphic memristive systems are to some extent challenging due to variability, due to a limited number of resistive levels and endurance cycles, and also the lack of computer-aided design tools that enable very large scale integrated systems. So floating gate flash memory devices have been in last years optimized, scaled down, and embedded in CMOS process. They are like their main advantage are technological maturity. So here, motivated by the technological maturity of floating gate devices and the conceptual efficiency of memristive devices, There has been like intensive research using floating gate devices by pioneering groups of memristive devices that use it to implement mixed signal very large scale integrated circuits for a neural network acceleration for inference. It's important to note that there are several startups that use such technologies to accelerate AI at the edge. So as I said, like motivated by the technological maturity of floating gate devices, we propose in collaboration with Tower Semiconductor, two-terminal floating gate memristive device that operates in the subthreshold domain, which is a power efficient operation mode. And it achieved excellent memristive characteristics. For example, 3 orders of magnitude current dynamic range, more than 64 distinct resistive levels. This device was implemented in a commercial CMOS process, which is implemented using single poly CMOS 180 nanometer. It also has mature characteristics with 100 kilo cycles for endurance and 10-year data retention. So we designed a chip using these devices. We designed a memory array, and we did a tape out at our foundry, and did functional bring up at the Technion at Shahar's lab. And one such demonstration that leveraged this chip and used it to demonstrate a real AI application and training at the edge was recently published in Nature Electronics, and proposed implementation and training using a restricted Boltzmann machine and deep belief networks. Actually, this kind of algorithm relaxes the requirements of the building blocks of both the data converters. Because the neural states are fully binarized, then it mitigates the exponential IV relationship of the floating gate memristive device, and mitigate also the expensive data conversion. Okay, so back to our ADC. Actually, I show here the memristive device that is ideal for our ADC application. So this ongoing work actually mounted discrete components of the activation neural components using discrete components, for example, operational amplifier, comparators, together with the floating gate memristive chip, in order to demonstrate a training of the ADC. And here, to deep dive into the microarchitecture of the ADC itself. So this is a trainable version of the ADC. Like each triangle here, it represents a tunable synaptic weight using Memristor and 2 transistors. And each triangle is a decision-making neuron. And each feedback here actually implements the gradient descent algorithm, which derives from the derivative of the error, which measures the distance between the actual ADC output and the desired ADC output. And this is some simulation results that show the efficiency of the algorithm in adaptation, in convergence into the desired specifications. So here, for example, we see the conversion of the training error into a predefined minimum. We also see the capabilities of this algorithm to self-calibration to achieve high accuracy of the ADC. And also another interesting feature that along with the training, also the power consumption is optimized. So in the broader scope of these collective capabilities of the training, actually we discussed to break through the speed power accuracy trade-off that we show in the first slide and enable a general purpose application ADC. We also extend this concept of ADC by using the same building blocks, the same methodology. We used also a trainable neuromorphic DAC. We took 4 bits of ADC and DAC and build a pipeline structure to obtain higher resolution ADC. So we believe that the findings of this research may constitute a milestone and valuable results for trainable mixed signal circuits, and to take these building blocks, memristors and data converters, to further steps to use them for analog and memory for AI acceleration. Thank you.